Hey everyone, in this video I'm going to be going over the solutions to the fifth free response question for you to work on AP Classroom. This one involves a Ferris wheel that is rotating at a constant angular velocity, and we're focusing on the inside of one of the compartments. We have a book sitting on top of a table. All right. So over here on the right, they've given us a graph that shows the horizontal position of the book as a function of time. And you can see we get this sine wave. This is one of the characteristics of uniform circular motion. If you look at just the x-coordinate or just the y-coordinate, it actually changes in a sinusoidal manner. All right, so we're basically given this graph and the fact that this Ferris wheel is rotating at a constant angular speed as our only starting information. And then we're asked a series of questions here, so let's go through those one by one. All right, so part A has two parts. The first one asks us to find the period of revolution of the book. So the period just means the time that it takes to make one complete revolution on the Ferris wheel, and we can figure that out from the graph. So if we look at just one complete cycle on the graph here, it goes out to this point here, which if you notice that each square on this graph is equal to 20 seconds, that gives us a period of 120 seconds. And part 2 asks us to calculate the tangential speed of the book. Now, if you try to determine the speed just by looking at the graph directly, you're going to have a pretty difficult time with that, and actually you're not going to be able to find the exact answer. So don't try to do that. Instead, use the fact that for something moving around in a circle at a constant speed, the speed can be calculated as the distance traveled divided by time. So the distance traveled for one revolution will be 2 pi times r, and then the time is the period that we just determined in the first part. Okay, so what is the radius? That information is actually a little bit hidden in this problem, but if you look at the graph and look at the vertical axis here, we can see that the horizontal position goes back and forth between minus 30 and plus 30. So as this thing is rotating, x equals 0 right here. When it swings out this way, we hit a maximum displacement in this direction of 30 meters, and then when it comes around the other way, we hit a maximum displacement of 30 meters in the other direction. So this graph here, these peaks being at plus and minus 30 meters tells us that the radius of this ride is also 30 meters. So we can plug in the values for the radius and the period. We get 60 pi over 120, or 1/2 pi meters per second. So you can actually leave the answer like that, or if you want to round that to about 1.6 meters per second, either way is fine. Okay, so part B starts to ask us a little bit about the forces involved here. So you're given a dot and you're asked to draw a distinct arrow on the dot representing each of the individual forces that are acting on the book when it is at the lowest point of its path. All right, so say this dot here represents the book. There's going to be two forces acting on it. There's going to be a gravitational force, which you can label as Fg or mass times g, either way. And then since the book is sitting on the table, there's going to be a normal force from the table pushing the book upward. So that will look like this. Now, notice I did not draw these arrows the same length. That's because these forces are actually not equal to each other. That's an easy misconception for this type of problem, where the book is at rest with respect to the table, but it is not at rest overall. It's moving around in a circular path, so there is an acceleration, and that acceleration must always point towards the center of the circular path. So in this case, that's going to be straight up. All right, this is actually part 1. So that explanation actually started to go into part 2 of B a little bit. So it asks you at the lowest point of the circular path, the book is moving only in the horizontal direction, but what direction, if any, is the net vertical force on the book? So the answer to this is the net vertical force is in the upward direction. The reason for that is that although the velocity of the book is in the horizontal direction, the acceleration is in the vertical direction. So we know that circular motion means that we have an acceleration which we call a centripetal acceleration, which always points towards the center. So if the book is at the bottom of the Ferris wheel, towards the center means straight up. Okay, so in part C, they want us to actually find an algebraic expression for this force. All right, so for that, we're going to have to look at this diagram that we drew in part B and apply Newton's second law. So Newton's second law says that the net force equals mass times acceleration. For circular motion, it's always a good idea to make the direction towards the center to be your positive direction and away from the center to be your negative direction. So in this case, the normal force will be a positive force and gravity will be a negative force. So the net force is going to be Fn minus mg, and that's going to equal mass times acceleration. For circular motion, the acceleration is always the centripetal acceleration, which is equal to v squared divided by r. So we're actually calling these mb and vb, I guess, so I'll be consistent with their notation. So here we're pretty much done. We're trying to find the normal force, that's the force exerted by the table, so I just move the mg term over to the other side. And I get something that looks like this. I guess if I wanted to, I could simplify this a little bit. There's a common factor of m in both of these terms. So I could also write it like this. And that is the normal force. All right, so I think there's one more part here. So question D just asks you to sort of analyze your results for the previous parts. So at the lowest point of the circular path, is the force that the bench exerts on the book greater than, less than, or equal to the weight of the book? So the answer here is greater than. And I want you to briefly explain how your answers to B part 2, which is the direction of the net force, and your answer to part C, which is this expression, support that answer. Well, first of all, let's look at part C. This expression here is clearly greater than m times g, right? So if we have mg plus some other term, the second term has to be positive because all of the values in it are positive. So that must be greater than the weight of the book. So that seems pretty straightforward. For part B, we said that the net force must be upward. Remember, the net force is the centripetal force. So that's one thing we could say here. Since the centripetal force must point towards the center, the net force also has to point towards the center. So that means the upward force has to be greater than the downward force so that the net force points in the correct direction. All right, so this problem had a bit of a review of circular motion, these concepts of centripetal force and centripetal acceleration. There are a couple of common misconceptions that could pop up in a question like this, so I just wanted to take a little bit of time to highlight those. There may be others, but these are the ones that come to my mind. So first of all, notice that if you have an object sitting on a flat surface, there's going to be at least two forces acting on that object, the gravitational force and the normal force. These two forces are not necessarily always going to be equal to each other. You have to ask yourself whether this object is accelerating overall. So, in the example of this problem, the book was sitting on a table. It's not moving with respect to the table, but it is moving in a circular path, so it is accelerating. There is a net force on it, so the forces acting on it are not just going to completely balance each other. Second potential misconception here is that the net force acting on an object is not necessarily in the same direction as its motion. So this came up in part B, subpart 2, where it said, the book is only moving in the horizontal direction, but what direction, if any, is the net vertical force? So you have to realize there that the book can be moving only in the horizontal direction, but have a net force only in the vertical direction at the same time. Those two things are completely compatible with each other, right? So the force or the acceleration and the velocity can be in completely different directions. So you may remember some sample problems that we looked at earlier in the year where we would have an object and say, what if the velocity is in this direction, but the acceleration is in this direction? What is the object going to do? And the answer to that is it's going to move in this direction, but it's going to change direction because of that acceleration. So it's going to sort of curve off to the right like this. So remember, normal force and weight of an object are not always the same, and net force and velocity can be in completely different directions and often are in different directions. Okay, so hopefully that clears up any questions that you had with this problem. If you still have any, feel free to send me a message. All right, thanks and have a great day.